Okay, in this video, we're going to continue with Kirchhoff's voltage law. Now this question says, find VO in the circuit. So we're going to have this circuit diagram. Now where is the voltage VO? Well, we know the voltage VO is going to be this voltage right here, which is going to be the voltage at these two terminals. Right away, when we identify the voltage VO, we should notice something. We should notice that the voltage VO is in parallel with this voltage source. And because these two voltages are in parallel, we know the voltage VO is going to be the same voltage at this voltage source, which is going to be 2VA. So therefore, right away, we can write an equation to represent VO. We can say VO equals 2VA. And we know that right away because these two voltages are in parallel. Now let's look at our circuit, right? We know VO equals 2VA. So now that we have this equation, we need to find what is VA. So where is VA? Well, we know VA is going to be right here, which is going to be the voltage at these two terminals. So we have options, right? Depending on what you want to do, you can go ahead and either take a KVL at this loop and at this loop, and then you should be able to find VA. Or you can take a KVL at the outer loop and then maybe take KVL at one of the smaller loops. It's really up to you on how you want to proceed. Now, if you haven't noticed by now, there are so many ways you can go about solving these problems, right? Whichever way you decide to go about it, you're always going to get the correct answer once you follow the right steps. Now remember, if you want to, you can do a KVL at this loop and a KVL at this loop. You can also take a KVL at the bigger loop. So it's really up to you how you would like to proceed. For me, I'm going to call this loop 1 and loop 2. So in this particular example, I'm just going to take the KVL at the outer loop. I'm going to write it as KVL at outer loop. Now I'm going to start at this 12 volt source here. I know when we walk in this voltage source, it's going to be a positive 12. And when we come around, we have plus Vx. So that's going to be the voltage in this resistor. The voltage in this source is going to be minus 4Vx. Now we're going to come all the way around. So now when we get to this particular element, there is no voltage label across this resistor. So what should we do? Should we just skip over it? No. What we're going to do is we're now going to label a voltage for this particular resistor, right? So for me, I'm going to write this as plus, minus, and I'm going to call it V1. So even though they did not label a voltage across this resistor, we know as we walk around this resistor, it is going to have a voltage drop. So I'm just going to label it plus to minus. Now remember, you can choose the polarity, right? I just chose it as a voltage drop. So in my KVL equation, I can now write the voltage across this resistor as plus V1. Now our last element is going to be this voltage source, and we're going to have plus 2VA equals 0. Now let's start to simplify this. We're going to have 12 minus 3Vx plus V1 plus 2VA equals 0. We have three unknown voltages. Because we have three unknown voltages, I want you to ask yourself, do we have one or more than one passive elements, such as resistors, capacitors, or inductors? In this particular situation, we do. We actually have two resistors, and both of those voltages we do not know, right? We have Vx, which is here, and we have V1, right? So we know Vx is going to be the voltage across this resistor, and we know V1 is the voltage across this resistor. Once you have identified that you have passive components, I now want you to write the relationship of the voltage for each of those resistors using Ohm's law. So for example, we know Ohm's law states voltage equals current times resistance, right? So when we look at this, we know to find the voltage in each resistor, we're going to need a current. Do we have a current label? No, we don't. So once again, we're just going to have to add in a current because we know a current is going to have to be flowing through this circuit, right? So once again, we have to use the basic knowledge of circuits that we know to solve this problem. We know there's going to be a current. Now you can choose the direction of the current. I'm going to draw the current in a clockwise direction. So I'm going to say the current is going to go this way. And I'm going to label the current I. So now that we have a current that we're saying is going in a clockwise direction, we can now write the relationship for the voltage in each of these resistors using Ohm's law. So for the voltage Vx, we can write that relationship as IR. And we know the current in this particular situation is just going to be this capital I. So we can write it as I, and the resistance is going to be 4 ohms. So we can just write 4. So when we simplify this, we can say Vx also equals 4I. So everywhere we see Vx in this particular equation, we're just going to write 4I. Now we have one more resistor, so let's write the value of that voltage using Ohm's law. We have V1, so we can say V1 equals IR. We know the current is going to be I, and the resistance is going to be 2. So we have 2. When you simplify this, V1 equals 2I. So these are two important equations we need to know. So everywhere in our KVL loop equation, we're just going to substitute in those voltages using the relationship between the current and the resistance. So we can say 12 minus 3. Instead of Vx, we're just going to write 4I. So we have 4I plus we have V1, which is going to be 2I plus 2. We still don't know what VA is going to be, so we're just going to write VA equals 0. Now when you start to simplify this, we're going to have 12 minus 12I plus 2I plus 2VA equals 0. This is going to give us negative 10I plus 2VA equals negative 12. Now we still have two unknowns, but there's nothing we can do at this point. So we're just going to move on. Now this equation could help us, or maybe it don't help us. We just have to continue to write KVL loops to see what's going to help us, and then we can start to simplify and solve from there. So let's do KVL at either loop 1 or loop 2. I'm just going to choose loop 2, right? So I'm going to write a KVL equation at loop 2. I'm going to say KVL at loop 2. I'm going to start at this voltage source right here. I know we're going to go into the positive terminal. So I'm going to write this as 2VA. We have 2VA. Now as we come down, we have a negative VA. So we have a negative minus VA plus V1. So we have plus V1. All of that equals 0. So let's simplify this. 2VA minus VA is going to give us VA plus V1 equals 0. Now when we look at this, we have two different KVL equations, right? We have VA plus V1, and we have negative 10I plus 2VA equals negative 12. Now these don't look the same, right? Usually once you have a situation where you have two equations and you have the same two unknown variables, all you have to do is use systems of equations. Now you might look at this and say, well, this isn't the same, so we have to write another KVL equation. But that's not true. I want you to keep track and be very mindful of what you're doing when you're solving these problems, right? We know we just found V1 in terms of Ohm's law, which is current times resistance, right? Just remember, if you know you have a voltage across a resistor, you always want to write it in terms of Ohm's law. So instead of writing V1, we know V1 equals 2I, right? So instead of V1, we can just write 2I. I'm going to write this as VA plus 2I equals 0. So let's solve the equation for VA. I can say VA equals negative 2I. Now this may be very important to us, so we want to keep it here. We're just going to mark that equation. Now what I'm going to do is, I'm now going to substitute in this value of VA into this equation to solve for one of the unknowns. So I'm going to say negative 10I plus 2 negative 2I, because we know VA equals negative 2I equals negative 12. When we start to simplify this, we have negative 10I minus 4I equals negative 12. Negative 10I minus 4I is going to give us negative 14I equals negative 12. Therefore, we can say I equals 6 over 7 amps. Now remember, the question does not want us to find the current, right? But we was able to find the current, and we know that's going to be 6 over 7 amps. The question wants us to find VO. We know VO equals 2VA, right? We know that because the voltage VO is in parallel with this voltage source, 2VA. So we know the voltage VO is going to be the same voltage that's in this voltage source, 2VA. So what we want to do is we want to find the value of VA. Now we just found the value of VA, which we know VA equals negative 2I. So let's use what we just found, which was 6 over 7 amps, to find VA. We know VA equals negative 2. I is going to be 6 over 7. So we're going to write 6 over 7. Now when you start to solve for this, VA equals negative 12 over 7. Now we know to find VO, which is the voltage they want us to find, we're going to have to multiply 2 by VA, which is this relationship here. Therefore, we can say, so I'm just going to write this equation over. We know VO equals 2VA. So VO equals 2 multiplied by negative 12 over 7. And that's what we just found right here. So when you solve for this, VO equals negative 24 over 7 volts. So this is going to be our answer for this particular problem. So we had to use the current we drew in, and we had to solve for VA in order to find our answer, which is negative 24 over 7 volts. Now, of course, there are multiple ways to solve this problem. You might have done KVL at loop 1, KVL at loop 2, and you might have been able to solve for VO that way. I think that way might have been a little shorter. But the purpose of this particular question was to show you if you're writing a KVL loop equation and you have a voltage across a passive element such as a resistor, capacitor, or inductor, you always want to write that voltage as it relates to Ohm's law. So we know Ohm's law is current times resistance. So anywhere you see that voltage, you're just going to write it as current times the resistance, given that you know either the resistance or the current. So just remember, the only way you can write that voltage as a relationship with Ohm's law is you must know either the current or the resistance. Let's do another example. So this one says find V1, V2, and V3 in the circuit. So in this circuit diagram, they want us to find the voltage across this resistor, the voltage across this resistor, and the voltage across this resistor. Now, unlike the first example, we don't know the value of these resistors, and we don't know the current. Therefore, when we write our KVL equation, we're just going to have to leave it as the voltage that they give us. So, the first thing we're going to do is label each loop. We know we're going to have 5 loops in all. I'm going to call this loop 1. This is loop 2. This is loop 3. This is loop 4. I'm going to start to take the KVL equation at each loop, starting at loop 1. So we're going to have KVL at loop 1. I'm going to start at this source right here. I know we're going to walk around and go into this source. We're going to have negative 4Vx minus 4 minus V1 equals 0. Now remember, we don't know the current or the resistance across this resistor. Therefore, we're going to be forced to leave it as this voltage. So when we start to simplify this, we're going to have negative 4 Vx minus V1 equals 4. Now there's nothing we can do to solve Vx or V1 at the moment. So now we're just going to have to move on and write another KVL loop. So this time we're going to write a loop equation for loop 2. We have positive 6 plus V2 plus 4 Vx equals 0. When you start to simplify this, we're going to have V2 plus 4Vx equals negative 6. Now once again, there's nothing we can do because we have Vx and V1 in this equation and we have V2 and Vx in this equation, so we cannot use systems of equations. So sometimes this is how it's going to be, right? You can write out different loop equations, but you just have to keep going until you have something you can work with. I'm going to write a KVL loop for loop 3. I'm going to say KVL at loop 3. That's going to give us negative 12 plus 4 plus Vx. Now we only have one unknown in this particular equation, so we can solve for Vx. Therefore, we can say Vx equals positive 8 volts. Now this is probably going to be important to us, so I'm just going to circle it. Now let's look back up at our KVL equations for loop 1 and loop 2. In this one, we have Vx and V1. So now all we have to do is substitute in the value for Vx into this equation to find for V1. And it's very similar for loop 2. We have V2 and Vx, so all we have to do is substitute in the value of Vx into this equation to find for V2. So let's do that. Now before I do that, I'm just going to pull this working down some. So I'm going to have negative 4. I know Vx is going to equal 8 volts, so we're going to have 8 minus V1 equals 4. Therefore, we can say minus V1 equals 4 plus 32 minus V1 equals 36. Therefore, V1 equals negative 36 volts. And this is one of the voltages they want us to find. So this right here is going to be one of our answers. Okay, now for this one, we know V2 plus 4, we know Vx is going to be 8 volts equals negative 6. V2 equals negative 6 minus 32. V2 equals negative 38 volts. So this is going to be the answer for V2. Now they want us to find one more voltage, which is V3. So we're just going to take a KVL equation at loop 4 to find the voltage across this resistor, which is going to be V3. So we're going to say KVL at loop 3. We're going to have plus V3 here. So we're going to have positive V3 minus Vx minus V2, and all of that equals 0. Now we know the values of Vx and V2, so we can say V3 minus 8 minus negative 38 for V2, right, equals 0. Therefore, V3 minus 8 plus 38 equals 0. V3 plus 30 equals 0. Therefore, we can say V3 equals negative 30 volts. So this is our answer for V3. Now that we have found the voltages V1, V2, and V3, we have successfully solved this particular problem. Let's do another example. So this question says, find Vs in the circuit. We know Vs is going to be the voltage source. So to find Vs in this circuit, we're just going to take a KVL at loop 1. We can write this as minus Vs. Now for this particular resistor, they do not label the voltage across this resistor. So I'm just going to assume it's going to be a voltage drop from plus to minus, and I'm going to call it V1. So I'm going to have plus V1. And across this resistor, there isn't any voltage labeled as well. But notice we have a voltage drop, which is labeled as VO equals 3 volts, which is going to be across these two terminals. But as we can see, this is going to be in parallel with this resistor, which means the voltage across these terminals here is going to be the same exact voltage across this resistor. So we know VO is going to be 3 volts here and also here. So for the sake of being thorough, I'm just going to write it as plus VO equals 0. Now let's start to simplify this. I'm going to have minus Vs plus, now notice we have a situation where we don't know the voltage across this resistor, but we know the resistance. Therefore, I'm just going to now draw in a current to go this way, and I'm going to label that current I. And instead of writing V1, I'm actually going to write it as a relationship between the current and the resistance, which is going to be 12,000 I. So we have plus 12,000 I plus, we also have a voltage across this resistor. Now instead of writing it as VO or even substituting in 3, I'm actually just going to write it as 9,000 I equals 0. So when we start to solve for this, we can say Vs equals 21,000 I. Now remember, they want us to find Vs, so we have to find what is I in this circuit, right? So let's write a KVL equation for this loop. I'm going to say KVL at loop 2. So we're going to have plus VO and I'm going to treat this as a voltage drop as well, right? So let me just label that in. We're going to have a plus minus, and we know we're going to go into the negative terminal, so I'm going to have minus 9,000 I equals 0. So when I solve for this, VO equals 9,000 I. Now, what is the value of VO? We know VO equals 3 volts. So we're going to write this as 3 equals 9,000 I. Therefore, when we solve for this, we can say I equals 3 over 9,000. When you put that in the calculator, you're going to get a recurring decimal. Therefore, we can say I equals 0.333 milliamp. Now, all we're going to do is write the value of I in the equation we have for Vs. So we can say Vs equals 21,000 I. I'm just going to use the fraction because I want to be exact. So we have 3 over 9,000. When you put that in the calculator, Vs equals 7 volts. So this is going to be our answer for Vs in this circuit. So Vs equals 7 volts.